Okay, all right, well, let's begin. We will continue our lectures on Markov chains. So on Monday, we introduced kind of just the idea of a Markov chain. And right now we were looking at discrete state, discrete time Markov chains. And for these things, we created a transition probability matrix that showed the kind of transition probabilities of going from one state to another state at the next block of time. And what we want to do is we want to kind of look at some of these properties, and one of the key ideas is that there are limiting distributions for some Markov chains. So for some Markov chains, we get, it's a loud door, we get a limiting distribution. And so let's just take this very simple example and take a look at this. I think this is the example we had for whether the weather was going to be sunny or not sunny. And we said if today is sunny, then there's a 80% chance that we stay sunny at the next time. And there's a 20% chance that we transition to not sunny. And right now we have 0 representing sunny and 1 to represent not sunny. And then if it's not sunny, then we'll say 40% chance of it being not sunny again, and a 60% chance of transitioning back to sunny or something. Or I don't know, maybe this isn't sunny, not sunny. It's just zeros and ones here, okay? Or A and B, whatever it is. And so what we want to know is, if we start the chain at x equal to 0, all right, so x at time 0 is equal to 0, and we just let it run for a long time, what will this chain look like? Okay, so there's a nice little applet that kind of shows what this Markov chain looks like here. Okay, and actually I can rotate this around a little bit. Okay, and so you can see the little ball kind of representing the state that it's in, and so you can see right now it's kind of on a loop going A to A to A, and that kind of makes sense because there's an 80% chance of it, if it's at A, it's going to remain A with probability 80%, and every now and then it'll, with probability 20%, it goes to B, and once it's at B, there's a 40% chance it goes back to B, and a 60% chance that it goes back to A. And so sometimes we see it go from A to B, back to A, and then we see it loop at A for a while. Let's see if it, okay, and there it goes from B, right? So, and you can kind of speed things up, right? And we're just kind of watching this thing. Now, I could also change, right? So if this wasn't 80%, but if I reduce this to, say, 50%, and 50% here, okay, now we will see it go from A to B more frequently. And the question is, if we recorded every stop that that the state goes in, what does the distribution of states look like, right? So we're going to get kind of a sequence of A's and B's and things like that. And we just kind of look at kind of the overall sequence of A's and B's. What does that thing look like? Right? So here we have, now, I can even do like 99% and 0.01, and you can see it's just going to stay at A for a very long time. Yeah, here, we can even do kind of like a, let me just do, let's reduce this to 90% and 10%, okay? And let's crank up the speed. And so when we do that, it's kind of, this is like 90% returning to itself, so it's kind of stuck in B. And then let's see if it gets stuck in B, it keeps wanting to go back here. Okay, now it's stuck in A for a while. 10% probability of kind of switching. So you kind of get this, you know, what does the sequence look like here, right? If we ran this like for 1,000 iterations, what's kind of the distribution of A's and B's? That's kind of what we want to know, okay? But I forget whatever our the original thing was something different. The original one was this. Okay, this app, it's pretty cool. You can even have like 3 states. You just have to, it uses Python NumPy notation. Did that not work? 0.1, 0.4. There we go. So now we've got 3 states and we're transitioning between A, B, and C. Okay, well, anyway, you can spend all day staring at this. It is a little bit mesmerizing. Okay, so here what I'm going to do is I'm going to just run a simulation. Okay, so I'm going to create my transition probability matrix 0.8, 0.2, 0.6, 0.4. And we're going to have, we're going to say, let's run this 100,000 times. Okay, and then X will start off at 0. And then we just have a bunch of NAs. Right? And we're going to just say for state 2 through whatever, okay? So the way I'm going to do this is I'm going to sample either a 0 or a 1, okay? And so what I'm going to do is I'm going to look at the previous row, the previous X. So for current iteration 2, we're going to look at X at position 1. Okay, this feels strange because R is indexed at 1, not 0. It's not a 0 index language. So you kind of have to keep adding 1s and subtracting 1s and things like that. Okay, so for the second iteration, we're going to look at the value in the first position. So X at time, I guess, I minus 1. And then we want to use the probabilities that correspond to that, right? So if X is 0, we're going to use the first row of probabilities. And if as X is equal to 1, we're going to use the second row of probabilities for its transition matrix. So we're going to say which row to use is going to be the previous X value plus 1, okay? And then I'm going to sample either 0 or 1, okay, using the probabilities that are specified in the either row 1 or 2 in the matrix P, okay? And so the sample function, you can specify the probability of getting a 0 or the probability of getting a 1. Okay, and then so I'm going to just let this run from 2 through 100,000, okay? And when we, at the end of our chain, I can ask how many times was it 0? How many times was my sequence 0? And it was 0 with around 75% probability, 0.7497, so I think 74,970 times. And it was 1, 25,030 times, so probability of around 0.25. Okay? And that was if I started at state 0. Okay? What if I had started with my first case was state 1? Okay, what if I had a different starting case? What if I started not at position 0, but at position 1? Does that affect things? Okay, so I run the same thing. I'm going to use a different seed. Using a different seed, I end up getting similar values, something around 75% for how often it was in state 0, and 25% for how often it was in state 1. Okay, and again, this is just kind of a, not that, oops. this is just letting this thing run. You know, we have state 1 and state 2. This would just be letting it run for a very long time to see, you know, how long did it stay in state A. And according to this, if you let it run for a long time, it's going to be in A around 75% of the time, 3/4 of the time it's at A, and about 25% of the time it's going to be at B. It's like going so fast there. Okay. So this is not a proof of any kind. We just did 2 iterations. I said starting at state 0, we got 75% at 0 and 25% at 1. Starting at state 1, we got 75% at 0 and 25% at 1. Okay? And so both simulations end up with approximately 75% of our values in state 0 and 25% of our values in state 1. And we can just specify a value, pi sub 0. This is the long run relative frequency that the chain will be at state 0. This is, if we ran this towards infinity, what is the proportion that we would get? Okay? And pi 1 will be the long run relative frequency the chain is at state 1. Okay? And so pi would be our limiting distribution, okay? And this would be a distribution on the state space. Our Markov chain only has 2 values, 0 and 1, for what states it could be. And so we want the distribution on this, and based on our simulations, we can guess that our limiting distribution pi is going to be 0.75, 0.25, 75% state 0, 25% state 1. So let's think about this, okay? So we can ask, what fraction of time is state J, or what fraction of time does the Markov chain spend in state J, whether that's 0 or 1, okay? And we're going to say the time that it spends in state J is going to be pi sub J, all right? And in our case, J can be 0 or 1, but you might have other Markov chains where you have, you know, J could be 0 through 20. So if pi sub 0 is 0.75, then that means our Markov chain is in state 0 around 75% of the time, okay? So the probability that x of n is in state j is going to be pi sub j. That is to say that as n goes to infinity, the probability that x at time n is going to be in state 0, given that the first value was at state 0, should be 75%. And also that as n goes to infinity, the probability that x of n is at state 0, given that the first value was some other state, in this case state 1, is also 75%. Okay? The idea is that when you go out to infinity, what happened on your very first day doesn't matter. Okay? What happened at state, your initial state, has no impact on where you are, what the probability is as you go out towards infinity. Okay? Now, this is not that if prior to infinity, it might not be, you might not have reached your limiting distribution, right? So it's kind of like, let's say, I don't know, we release something stinky right up here, okay? Something stinky happens, okay? And we can say that the diffusion of molecules follows kind of like this Markov chain, right? It's kind of like this random walk. Each molecule, each stink molecule is flowing through the air in this random walk, right? So immediately after this smell has been released, this odor has been released, immediately after, the concentration of smell is right around here, and then those far away will not have smelled it yet, right? But then you give it a lot of time, and it will diffuse, right, out throughout the room, and if we ask, where was the odor released, right? If you come back and if you're still able to smell it, like, I don't know, in half an hour or an hour or whatever, and we say, hey, where was it released? You would not know where it was released because, you know, the smell is everywhere, right? It's kind of like, you know, if there's a skunk and you smell it. It's hard to, well, at least as humans, we're not dogs, and we can't go and then say, you know, it's stronger in that direction than it was in that direction, right? That's like the amazing thing about dogs, is that their noses are so sensitive they can detect the small differences between kind of the diffusion of smell. You know, we don't have that sensitivity, and so anyway, we're not able to kind of detect any difference, because at this point, you know, as time goes to, well, not infinity, because by infinity then it would have diffused out through the windows and everything out into the world. But you know, at some point within, if it's still contained within the room, it would have been very spread out. Okay, and the idea is, you know, it doesn't matter exactly where it's initially released or the initial value, just that after a long period of time, the probability of it being in some state is going to just be its limiting distribution. Okay, and so we're going to just say that if you have some state space, if you got n possible states, in our example we just had 2 states, 0 and 1, but more generally you can have n of these different states. Your limiting distribution pi is going to be, you know, some vector of n values, and if you add all of those up, you're going to, you know, they'll add up to 1. Okay, and we're going to say pi is the limiting distribution of the Markov chain if, okay, if the probability that x is in some state j is equal to pi sub j, regardless, okay, of where you started, regardless of where you started. And so this has to apply. So you might not have a limiting distribution. So some Markov chains don't have limiting distributions because depending on where you started, it might not be possible to reach state J. Okay? So if we're talking about, you know, ending up on some location, right? It's depending on where you started, certain things might not be possible, right? You might not be able to reach one of the states if you started somewhere else, okay? So, but we're going to say that if the limiting distribution does exist, then this pi sub j represents the probability that our random variable x is in state j, you know, at some arbitrary time n in the future, that that a random value is in state j, independent of the initial state, okay? And this is going to be the long run expected fraction of time that the Markov chain spends in state j. All right, let me go ahead and give you your first view quiz answer. Today's first view quiz answer is the letter B. B as in bear. B as in bear. We have something called the stationary distribution. All right, the stationary distribution is a distribution over states such that the expected distribution of the Markov chain at the next time is the same. Okay, well, all this means is that this is the distribution of the system at equilibrium. Okay, and this is basically, if you have a limiting distribution of a Markov chain, then that limiting distribution is the stationary distribution. Okay, the limiting distribution is the stationary distribution. So if you think of not just individual states, okay, so in our little app, we've got the individual state moving, but if this kind of represents like populations moving about, or not populations, but entire kind of groups moving about, then the stationary distribution will represent what's happening to our states at equilibrium, okay? And we have this theorem that says if the Markov chain is ergodic, it will eventually converge to a stationary distribution. Okay, so I have to tell you what ergodic even means. And you know, you can really get into ergodic theory on Markov chains, and you can take an entire course or series of courses or spend your entire life studying properties of Markov chains. But here you're going to just kind of get your condensed down 25-minute summary of this ergodic theory. And so I titled this Informal Definitions of Markov Chains, just because we're not going to do this mathematically rigorous kind of proving of the stuff, but I'm going to appeal to your intuition, and hopefully that will be at least kind of satisfying for now, okay? So we're going to say a Markov chain is said to be ergodic if we can start the chain at any of the possible states, right? So if you imagine a Markov chain with different possible states, it's ergodic if you can start at any one of those states, and then at some arbitrary time in the future t, okay, and this arbitrary time in the future could be like thousands of years into the future. It could be a really long time, but we're just saying at some arbitrary finite time in the future, at some finite time in the future, at arbitrarily big, whatever, okay, then the probability of being in any of the other states is greater than 0, okay? That is, it's possible to reach any of the other states, okay? It cannot be 0. So if you start, basically if you start in one corner of the world, if we had an ant and we put it in one corner of the world, could it reach everywhere else? Everywhere else in the world? And, well, what about everywhere else on land? And the answer is no, okay? If you have like a little insect crawling around, it can walk around, assuming it doesn't get eaten along the way. You know, if you release them in Los Angeles, maybe this little ant can reach somewhere all of North America, maybe even South America, but probably can't cross the oceans, right? And so anyway, that would not be ergodic as far as all of the land, because we would not be able to reach, say, Australia, okay? But the idea is you can start at any location and then just end up somewhere else, right? So this must be true for all t greater than some finite integer t0, okay? So it just has to be true at just some arbitrary time in the future, just not infinitely in the future, okay? And the theorem is basically for it to be ergodic, for this to be true, the Markov chain has to be irreducible, which is a little bit of a strange word to describe what it means, and aperiodic, okay? So a Markov chain is irreducible if all states communicate with each other, all right? A Markov chain is reducible if it's not irreducible, okay? That's what it means here. If it's not irreducible, then that means it's reducible. And basically we're saying two states communicate with each other. If there is a path, even if it has to travel through a bunch of other states, if there is a path to get from state I to state J, okay? So in this case, if we have states 0, 1, 2, 3, 4, this state is irreducible because wherever you are, starting at state 0, it is possible to reach state 1, 2, 3, or 4, okay? If you start at any other state, it's also possible to reach any of the other states, okay? All of the states, it is possible, wherever you start, it's possible to reach any of the other states, okay? So this would be irreducible. All of the states communicate with each other. If you start at any of the states, you can find a path, okay? Even if it has to go through other states, you can find a path to get to any of the other states. This one is not irreducible. This one would be a reducible chain. All of the states do not communicate with each other, right? If you start at states 0, 1, or 2, there's no way you will end up in states 3 or 4, okay? So for any chain that begins in states 0, 1, or 2, this Markov chain diagram could be reduced to just those 3 states, okay? So I don't know. That's kind of the idea here. For a reducible chain, if you start over here, you know, these things are basically unnecessary, right? There's no way you're going to reach states 3 or 4, so don't even bother including those. Okay, so that's kind of just the idea of irreducibility, that you can reach any other state from something, okay? And then the other part of a chain being ergodic is that it has to be aperiodic, okay? So what is the period? The period of a state, okay? the period of a state is the greatest common divisor of n, being the number of steps you can take and end up back at the state itself. I can't, right? So how many steps will it take to end up back at yourself, okay? So let's take a look at state 3. If we start at state 3, there are lots of paths to get back to state 3, okay? There's lots of options, all right? So you can go from 3 to 2, back to 3. So that was a total of 2 transitions. You transitioned from 3 to 2, that's 1 step, 2 to 3, the second step. So that took 2 steps, okay? And you can go from 3 to 4 to 3 to 2 to 3, okay? All right, and so that would be 4 states. And you can say visiting your own state before ending at the state is also allowed, okay? So how many steps did it take to get back to 3 that time? We went from 3 to 4 to 3 to 2 to 3, total of 4 steps, okay? You can go 3 to 2 to 1, back to 2, back to 3, okay? So you went through 4 arrows there, that would be 4 steps. Okay, you can go 3, 2, 1, 0, 1, 2, 3, okay? And you have a total of 6 steps. You went through 6 arrows to get there, okay? And if you look, and if you try to, you know, obviously there's infinitely many paths that you can take because you're allowed to kind of visit yourself before. But if you look at these steps, either you took 2 steps, 4 steps, or 6 steps, or 8 steps, or something, the greatest common divisor for all of these things will be 2. There's no path, you cannot get back to state 3 in one state, in one step, okay? You can't get back to 3 in 3 steps. There's no way, you cannot take an odd number of steps and end up back at your starting point, okay? And if you look at any of these things, if you want to end up back at your starting state, you have to take an even number of steps, okay? And so this chain has a period of 2, okay? This chain has a period of 2. Because the greatest common divisor for the number of steps to get back to your starting state is 2. Does that kind of make sense, that this has a period of 2 here? Okay? All right, what happens if I just add this one thing, where I say, you know what, in state 4 has the ability to kind of transition back to itself. Okay? So then we can, looking at state 3, we can go to 3 to 4 to 3, 2 steps. We can go 3 to 4, back to 4 to 3, okay? And that will be 3 steps. And we can go 3, 2, 1, 2, 3, that's a total of 4 steps. We can go 3 and then 4, 4, 4, 4, and then back to 3, and that would be 5 steps, right? We can just keep looping back at 4, right? And you say, you know what, I want you to get back to 3 in 78 steps. And you can kind of enter cheating mode and you just go 3 to 4 and then you just loop around 4, you know, 76 times or whatever it is, and then you get back to 3 and you go, ta-da, I did it, 78 steps. It's not even, it's not hard, right, when you have it like that, okay? And so now, you can pretty much achieve any number of, number that you want to get, right, over something, right? And so the greatest common divisor here is just 1, okay? You can get back to 3 in 2, 3, 4, 5, 6, right? It's fine, we can't get back to 3 in just 1 step, but we can get there in 2 steps, 3 steps, 4 steps, 5 steps, so on and so forth. So this has a period of 1, okay? And then if we look at any of these other starting states, okay, again, we can kind of just abuse 4 and visit state 4 as many times as we want, okay? And all of these would have a period of 1, and the entire Markov chain would have a period of 1. All right, so Markov chain is aperiodic if all the states have a period of 1. If all the states have a period of 1, then the Markov chain is aperiodic, all right? And kind of on a practical level, if a Markov chain is irreducible, meaning all the states can communicate with each other, and if at least one state can go from it back to itself directly, kind of like this, if at least one of these states can go back to itself directly, then the chain is going to be aperiodic, right? And so if you have an irreducible chain, and at least one of the states can kind of talk to itself, or transition back to itself, then it's aperiodic, and then your chain is going to be ergodic. If it's irreducible and aperiodic, then your Markov chain will be ergodic. Okay, second view quiz answer today is the letter D. D as in dog. D as in dog. Okay, so here we have our two-state Markov chain, where we say we can go from 0 to 1. This is irreducible. Every state communicates with each other. And it's aperiodic because at least one of the states, both of the states, can actually communicate back to itself or transition back to itself. So if you look at how many steps does it take to get back to itself, you can pick any integer and get there. So this chain is going to be ergodic, which means it has a limiting distribution, and that limiting distribution is going to be the stationary distribution. Okay, so kind of all of these terms. So if everything communicates with each other, meaning it's irreducible, the period is 1, okay, meaning it's aperiodic, and then it's ergodic, which means there's going to be a limiting distribution, and that limiting distribution is the stationary distribution. So we want to figure out the stationary distribution where there's equilibrium between the states. That is, the probability of transitioning from state 0 to state 1 is equal to the probability of transitioning from state 1 to state 0. I guess it should be the probability of being in state 0 and transitioning to state 1 is equal to the probability of being in state 1 and transitioning back to state 0. Because obviously these arrows are different. We got 0.2 going this way and 0.6 going that way. But at some point, we can kind of reach equilibrium, okay? So if you're already at state 0, then the probability of going to state 1 is 0.2, okay? So it's very easy to see with the arrow. How do we express this? This is written as P01, right? This is this corner over here. So row 0, column 1 is 0.2, and that's the probability that at time n plus 1 that you'll be in state 1, given that at time n you're at state 0, that value is 0.2. And therefore the total probability of transitioning, of kind of being in state 0 and transitioning to state 1 is going to be the probability of just starting off at state 0 multiplied by the probability of transitioning to state 1, given that you're in state 0. And so that's going to be P0, the probability of being in state 0, times P01, which would be the transition probability of going from 0 to 1. Okay? Is this okay? I know there's a lot of P's and zeros and ones here, but hopefully you understand this value, P0, representing the probability of just being in state 0 in the first place. Okay? And then, and kind of going the other way, there's a 60%, 0.6 probability of going from 1 to 0 if you're already in state 1. And so the total probability of transitioning from state 1 to state 0 is a probability that you start off in state 1 and that you end up transitioning over. So it's going to be P1 times P10. And basically we want to figure out where is this going to be equilibrium? Where is basically the total amount going from here to here equal to the total amount going from here to here? Okay, so we want to figure out the distribution pi 0, pi 1, such that basically the amount going from 0 to 1 is equal to the amount going from 1 to 0. Right. So we know, just replacing P01, the transition probability of going from 0 to 1, that value is 0.2 from the matrix, right? This is 0.2, or that's this probability. And then the other P10 is 0.6. Okay, so we have 0.2 times pi 0 is equal to 0.6 times pi 1. And we also have, we know this is the stationary distribution, so that the states pi 0 and pi 1 have to add up to 1, okay? So yeah, you just have to do a tiny bit of algebra here. I kind of left it off the page, but I don't think it's that hard, okay? So if you do this, right, you can say, okay, pi 0, if I divide both sides by pi 1 and divide both sides by 0.2, we get the ratio pi 0 over pi 1 is equal to 3. And then solving for that, you know, plugging in pi 0 is equal to basically 3 pi 1. Okay, you get pi 1 is equal to 0.25 and pi 0 is equal to 0.75. Okay, so just using algebra to solve this, pi 0 is 0.75, pi 1 is 0.25. Okay, and so that's our stationary distribution. We are saying that if you have 75% in state 0 and 25% in state 1, after you apply the transition probability matrix, you're going to end up getting back your original starting distribution. Okay, so if we have a 75% probability of being in state 0 and a 25% probability of being in state 1, we can take our current distribution, multiply it by the transition probability, and see what resulting distribution do we have, right? So out of so 3/4 of the people are in state 0, and of those 3/4, 80% will remain at state 0, okay? And then 25%, 1/4 are at state 1, and of those 25%, 60% will also go to state 0. So the total amount going to state 0 is going to be 0.75 times 0.8 plus 0.25 times 0.6. So a total of 0.6 plus 0.15, or 0.75. Okay? All right, if we think about who's going to end up in state 1 at the next stage, okay? Well, we have 20% of the people who started off in state 0 will end up in state 1, okay? And 40% of those who started off in state 1 will also end up back at state 1, okay? And when you do this probability, 0.75 times 0.2 gives me 0.15, 0.25 times 0.4 gives me 0.1, and that will add up to 0.25. So we end up at the next state, you know, some people move around, but we still end up with 75% in state 0 and 25% in state 1, okay? Let me just kind of skip forward to just illustrate this. So I think I want to do, how do I get 25%? Oh wait, now what was it? 0.6 and 0.2, right? It's so hard. I don't know how to, I need to get this, the transition probability. All right, well, I'm not going to get the thing perfect, okay? Kills me. Okay, well, anyway. So this says there's two populations, California and New York, okay? And the idea is if I hover over this, California is represented with 38 million and New York has 19.65. And we're going to say, to kind of represent what we have here, if you're in California, we're going to say 20% probability of going over to New York. If you're in New York, 60% probability of coming over to California. Okay, I know these are not realistic numbers, but we're just going to go with it, okay? And then so watch what happens. So we start off with 38 and 19. And so so we're saying some are going to transition from 80%, we say around 80% of California stay and 19-20% go. And over here around 60% transition from New York to California, and only about 43% stay, okay? And so, let me just resize this to be really small. So we can start off with, almost everyone starts off in New York and just a few people in California start, okay? And we're gonna have 80% of California go over to New York, and only 40% of people in New York stay, and 60% will come over to California. And so what happens? So in the beginning, just one goes over, but then it keeps, we keep applying this transition, and eventually we reach equilibrium, where the number of people going from California to New York is equal to the number of people coming from New York to California, right? And so we have reached this equilibrium, and when you have this ratio of, say, 20% going from California to New York and around 60% going from New York to California, this is what you have, okay? If it's something like this, okay, where the 90% of California goes to New York and 30% of New York goes to California, okay, eventually we'll reach some equilibrium, okay? Or 90%, but again, we've reached equilibrium where the sheer number of people moving over is the same, okay? And again, we can kind of just play around with these things. And eventually we'll reach an equilibrium. Takes a little bit longer to get there. I think at this point you can even start counting. You can see that there's going to be like 7 people or 8 people, I don't know. 8 people transitioning from one side to the other side. Okay. So what does this look like mathematically? What's going on? Okay. Mathematically, we have pi, our vector pi, times the matrix P is equal back to pi. Okay? This is what we call, pi is the left-hand eigenvector, the left eigenvector of the matrix P. Because the eigenvector of a matrix is where you take the matrix, you multiply it by the vector, right? And you get back basically a scalar multiple of the vector. Okay? So we have you take the matrix times the vector, it's usually A times V is equal to lambda times V, is often how this eigenvalue thing is presented, okay? And usually the matrix is on the left-hand side and the vector is on the right-hand side, okay? And so that's your normal eigenvector is matrix A times eigenvector V is equal to some scalar value lambda times V. This time we've got some vector pi times matrix P is equal to the scalar 1 times pi. Okay? It's also another form of an eigenvector. It's called the left eigenvector. Okay? And so, yeah, the right eigenvector is the solution to this. Basically, the left eigenvector is equal to the transpose of the right eigenvector of P transpose. So if you take matrix P and you transpose it and you find the right eigenvector, then and you take the transpose of that, that's going to be the left eigenvector. Okay, so all we have to do is we can take our matrix P. We have the function eigen in R. Eigen finds the right eigenvectors. That's kind of your normal eigenvector solution. So we can just say, okay, take the matrix P, our transition probability matrix P, let's take the transpose of it. Let's get the eigenvectors of that. This is going to give us the right eigenvectors. And all we're going to do then is we are going to keep the first column. So it gives us the first column And this is, they're normalized so that the, when you add up the squares add up to 1. But here we're going to scale them so that the values themselves add up to 1. So we'll keep the first eigenvector, 0.948, 0.316. Okay? We will transpose them back to give us our left eigenvector. And to get them back to get a sum of 1, we're going to just take these numbers and divide by the sum of the numbers, so that these two values will add up to 1. And so when you do that, you get 0.75 and 0.25, which is basically your stationary distribution. So you can find your stationary distribution by finding the left eigenvectors of your transition probability matrix P. Okay? Does that kind of make sense, what's happening here? Okay, because again, pi, this vector, is the solution to pi times the matrix is equal to pi itself, okay? The vector pi itself. And that's just another form of matrix times the vector is equal to 1 times the vector. It's just, we're doing it on the left side, that's the left eigenvector. Okay, and so we had this visualization kind of showing how it worked. And so the next thing that we're going to do, and this is why we brought up Markov chains in the first place, okay? So what we saw today was we saw that if you have an ergodic Markov chain with some transition matrix P, you get some stationary distribution pi. And the idea is that if you run the Markov chain long enough, right, it doesn't matter what your starting thing looks like. Okay, we can start it off like this. Okay? And eventually, it takes a little while to get there, but eventually you're going to reach your stationary distribution, where after you keep applying those transitions and you talk about how many end up, then you end up in this kind of state of equilibrium, and basically the distribution of how many are in this state versus this state reaches a stationary distribution, okay? So if we let the Markov chain run long enough, it's going to converge to the stationary distribution, and then from that point on, the values that it generates will come from the stationary distribution. All right, so what we want to do next is we have some target probability distribution in mind. Okay? We want to be able to generate samples from some target probability distribution. Because this is kind of the whole idea, is we want to be able to generate values from some random distribution. Can we figure out a Markov chain? Okay, that is, when you're designing the Markov chain, it's entirely determined by its transition probability matrix. Can we figure out what the transition probabilities should be so that the stationary distribution of some chain is equal to some target desired distribution? Okay, this is what we want to do, right? So we've got so far we've been saying, all right, we can generate that random values from, using R norm, R beta, R gamma. If we can't do that, we do inverse CDF. If we can't do that, we do rejection sampling. And if we can't do that, this is the next thing that we turn to, a Markov chain. And we want the Markov chain to be designed in such a way that its stationary distribution is the desired target distribution. It seems so strange just because this Markov chain in the first place seems very abstract in the first place. But the answer is yes, we can do this. We can figure out what the transition probabilities will be so that if we let the Markov chain run long enough, the values that it generates will be equal to the target probability distribution. Okay, and that's what we're going to look at next. Okay, let me go ahead and give you your final view quiz answer for today. Last answer is A as in apple. A as in apple. Okay, we will end here. See you guys on Friday, and have a good day.